All right, thank you. So like the chair said, I'm Joe Cutler. I'm going to be talking about improving the stability of type soundness proofs in Dafny'. This is joint work with Mike Hicks and Emina Torlak. So I want to start this talk with a quick story. The story begins 2 years ago at the beginning of my internship at Amazon, where Mike and Emina sit me down and say, can you prove the type soundness of this language that we've been working on? And I say, yep, definitely can do. And they say, so we have an interpreter that's been written in Dafny', why don't you do the proof in Dafny'? And I, slightly overconfident first-year grad student, say, sure, sounds like no problem, sort of mentally thinking, this can't possibly be that hard. Smash cut to 2 years later, I'm standing in front of you today to talk about why proving type soundness in Dafny' actually was quite hard and how we managed to do it in the end. Okay. I want to set out sort of a toy language as an experimental platform to demonstrate the work that we did. This work was actually done on the Cedar language. For those of you who are familiar with Cedar, maybe you're Amazon people, think about Cedar. Otherwise, think about a toy language that has arithmetic, sort of Booleans and conditionals, records. It's sort of first order. There's no lambdas, nothing like that. It's terminating, so there's no recursion. It's a fairly straightforward language. The interpreter is written as sort of a definitional interpreter, big step style, that is a function written in Dafny' that takes an expression e and returns either a value, which is the value that the expression evaluates to, or some kind of evaluation error, which looks like either a runtime type error, you tried to add an int in a string somewhere, or maybe a divide by zero error where you did something wrong that maybe the type system couldn't catch. They also have written in Dafny' a type checker, right? A function check that takes an expression and a type and either returns sort of okay, that type checked, or maybe a typing error. The safety property that we're going to be interested in for the purposes of this exposition is that is this one, that E, an expression, is safe at a type t if when you run the evaluator on the expression, one of two things happens. Either E evaluates successfully to some value, and then the value that you get out at the end actually does in fact have type t, that's case one. And then case two is when you run the evaluator on the expression, you get like a divide by zero error. Okay? And so the type soundness theorem that we're interested in proving here just says that when you run the type checker on E and T and you get back okay, then E is safe as a value of type t, i.e. it either runs successfully or it errors with an error we can't possibly catch statically. Cool? So to prove this in Dafny', we just sort of encode it as a lemma with the precondition that check succeeds, and with the postcondition that is safe holds. Okay. So our first attempt at this was basically direct proof, right? To discuss how the direct proof should go, I want to take a look briefly at how the evaluator works and how the type checker works to sort of get a flavor of this. So the evaluator is written in, like I said, sort of direct recursive style, sort of like a definitional interpreter. I'm going to use the case of the add operation. I'm going to use the case of the, I might be using old syntax here or something. I'm going to use the case of the add operation, just sort of illustrate what I'm talking about. Imagine this extended for hundreds and hundreds of cases for all the constructs in the language. Okay. So in the add case, to evaluate an add expression, we first evaluate one branch, then we evaluate the other, we check that they both evaluate to ints, and then we return the int that is their sum, right? Straightforward. The checker, also just sort of standard direct type checker. Again, I'm going to look at the add case. We check that E1 and E2 both have type int, the two branches of the add. Then we're going to make sure that the type we're checking the add expression against also is an int. If all of that's true, then we return okay. Otherwise, we return a type error. Okay. I want to briefly take a look and illustrate just sort of at a high level without diving into the Dafny' how the proof of the add case of the type soundness theorem should go. So we start by assuming that calling check on add and t returns okay. Then sort of the solver is going to unfold the definition of check and get to the fact that E1 checks against t and E2 checks against t, and then we also made it to the correct branch of the if, the one that returned okay, which means that t has to have been equal to int. Then by applying the IH twice, the induction hypothesis twice, we get that E1 is safe at int, E2 is safe at int. And then unfolding the definitions of is safe and eval and sort of reasoning through things, we get that E1 plus E2 is itself safe at int, right? This is basically because one of three things can happen. Either E1 and E2 both evaluate to ints, and so their addition does as well, or one of them evaluates to divide by zero error, and so the whole thing blows up in the end. We can encode this in Dafny' just by writing down the two recursive calls to apply the induction hypotheses to E1 and E2. This is actually quite slick. Just apply the IH Dafny handles getting from check to check of E1 and E2, and then from safety of E1 and E2 to safety of the conclusion, right? This is really great. There's a big problem here, though, and this is where we got pretty stuck. This is super unstable in the sense that when you're trying to build this proof of hundreds of cases, you start working on one case, and you finish it, and you get the little satisfying green check mark in VS Code. And then you go on to moving to do case B. You fill in case B, and you get the little check mark there. And then you go back and you look at case A, and case A now has the red X next to it, and it failed to verify. Right? The proof, the outcome can change dramatically as you change the proof itself, which is really quite frustrating. And this is the part where I step back and say, oh God, what have I gotten myself into? This is way harder than I thought. And our hypothesis about why this particular proof is unstable is mostly because the solver has to reason about two very large definitions simultaneously, right? This check function and this evaluate function are both quite large definitions with lots and lots of cases that are both monadic. So we stepped back and we're trying to figure out how can we come up with a more robust solution, because at this point it was not clear that we were actually going to be able to complete the proof unless we could find a way to make this stable. It just wasn't feasible. Right? So you go talk to various folks, and as we saw in the last talk, the answer to an issue like this is to opaquify and specify. Right? Find some definitions, make them opaque, give them specifications, only let the solver reason about them through the specifications. But we really ran into a conundrum here, which is what are we supposed to make opaque? Right? Check and eval are the two functions involved, and they're both sort of like do what they do kinds of functions. They don't have obvious total specifications that we can use to reason about their behavior, okay? So I want to go back to the proof for inspiration, and in particular I want to take a look at the last step of the proof. And I want to think about to complete this case of the proof, what do we need to know about the safety property? It turns out that the only thing we need to know about the safety property in this case of the proof is that E1 being safe at int and E2 being safe at int jointly imply that add E1, E2 are safe at int. And that's the only fact that you need to know about the safety property. In fact, you need to know nothing about eval to complete this proof. All you need to know is that fact about the safety property. And so this gives us the spark of inspiration that we can just make is safe, the conclusion of the theorem itself, opaque, and then manually prove these safety lemmas, saying that E1 being safe at int and E2 being safe at int jointly imply that add E1, E2 are safe at int for all of the constructs in the language. And this proof basically follows the structure that I said before, right? Either they both successfully evaluate, or one of them errors, and so the whole thing errors. And this is and then you take those safety lemmas and you insert them directly after the calls to the recursive calls in the proof, okay? This is much, much more stable. The reason is that the solver now only has to reason about check. It can't look through the body of is safe to look at the definition of eval, okay? I want to quickly touch on what's actually going on here. Some of you might have noticed that all we're doing here is we're using the induction principle of the type system as it was designed. So the type checker, that function that we wrote in Dafny, really implements some inductive relation, right? So the check function is really a decision procedure for some inductively defined relation E has type T, which was written on paper, hopefully somewhere in a document that has a bunch of inference rules on it. And this basically tells us that the induction principle of the type system means that well-typedness implies any other predicate that interprets the rules of the type system. What do I mean by that? Let's say that we have some predicate P, and we're trying to show that E has type T implies P of every expression in term. To understand this, let's take a look at a case like add. We look at all the rules, we invert them to get that their premises hold, we apply the induction hypothesis to get that P holds of the premises, and then all we need to know to complete this case is that P holds of the conclusion, assuming that it holds of the premises. This is what I mean by well-typedness implies any predicate that interprets the rules. If we can do this for all the rules in the system, then P holds of every well-typed term. So the upshot here is that if is safe is opaque, but still interprets all the rules of the type system, then all well-typed programs are safe. Okay? A quick question that you may be having is can we go further? There's a whole other half of the proof that maybe we can leverage as well. And the answer is yes. We can play the same game again and notice that the only thing we need to know about the check function to make this case of the proof work is that if an add checks against t, then E1 checks against the type, E2 checks against the type, and the type is equal to int. And so we can play the same game again by making the check function, the type checker itself, opaque, and then proving these inversion lemmas, basically, for all of the rules in the type system. In a sort of nice little twist of fate, all of these inversion principles are sort of automatically provable. You don't have to write any assertions for any of them. And then you take these inversion lemmas, you insert them before the recursive calls, and you get even better proof stability behavior out of this. So I've been saying, we do a thing and it gets better. And then you may say, okay, Joe, how am I supposed to, what does that mean? I have two answers. One is a real answer and one is a glib answer. Let's start with the glib answer. The glib answer is that the Cedar soundness proof actually works, okay? When I was doing this work, it was not at all clear that we were going to be able to finish the proof in Dafny, and we might have had to bail out. But we did manage to soldier through, and with these sort of techniques that we developed, or employing these opacities and specificities, we were able to complete the type soundness proof. So I finished a type soundness proof for the sort of an initial version of the type system for this language. Here, over here on the right, you can see the current publicly available on GitHub top level type soundness theorem for the language. This is hundreds and hundreds of lines of code, but it all follows this structure. I was not the one that did the rest of this work. Other people did the rest of the work. The second answer, the real answer, is how much better, sort of quantitatively, is the proof stability of this. So we played the same game, of measuring verification stability by way of resource usage. So here I ran some experiments on the toy language that I developed for the purposes of this talk. These aren't graphs about Cedar itself, but I wrote 5 different versions of the type checker and 5 different versions of the proof, 5 different versions of the proof, and then measured the resource usage over 500 verifications of the VCs generated by the soundness proof. So the 3 that are relevant for the stuff I talked about in this talk are basic, which is sort of the direct style version, opaque safe, which is the version of the proof that has the safety property opaque, and opaque safe invert, which is the version of the proof that has the safety property opaque, the type checker opaque, and the type checker opaque. Okay, so the different soundness theorems are on the x-axis. The y-axis is the mean resource usage in factors of 10 to the 6th. So that's 10,000 or 100,000 or something like that. But relative scale is what matters here. You can see that the basic theorems have the basic theorem has significantly higher mean, but also more importantly the standard deviation, the variance of how many resources the solver takes are significantly fewer for the opaque versions. I didn't actually know about this coefficient of variation thing until 20 minutes ago during the last talk, but I computed them, and we can see, in fact, that the opaque safe one is less than 0.2, and the direct proof is bigger than 0.2. So that's good.
You mean 1.8 minutes, not 1.4 seconds?
Oh, sorry. I apologize. The S and the M, those. I apologize. Those M's stand for millions. Yes. And that should not say S. At one point, a version of this talk had times, and now it's resource usages, and the pre-post suffixes got mixed up. So let me end the talk there, and then I'll take your questions. Thanks. Am I on time? What was that time-wise?
Thank you. That was a very interesting talk. So this talk and the last talk has really implied that you're both fighting Dafny to get things to work. Now, and so the question is, what would you like to see change in Dafny to make your life easier? Great question. So I have 2 answers to this. One is an answer that I would have given you 2 years ago when I was working on this. I would have said, please just let me do this in Cocker Lean. Now I will tell you that the proof that I showed on the second to last slide is actually out of date, and it's all been redone in Lean. My contention about this kind of proof is that
for this sort of thing, mechanized meta theory, you probably shouldn't do this in Dafny because they're fairly manual proofs anyways that follow this regular structure that Dafny struggles to infer sort of directly. But I do think that the overall structure of if I could comment on the last talk, which was great by the way, I do think that like specifying and making opaque the definitions that you have in your development is like a very cut and dry, straightforward way to improve the stability, right? It worked like a charm. And I think that personally the trade-off of losing some of the automation to gain stability is very much well worth it because you sort of know what the proof should be to some extent when you're doing it, at least in my case.
Thank you. So I guess this is also a question for this talk and the previous talk. Mm. You both use the metric of the resource count of Z3 or the runtime. And this is something that's very empirical and not that meaningful for the user. I'm wondering if there is some metric that can be more meaningful for the user to say, these are the guidelines you should follow, like how many definitions the VC includes, how many quantifiers are needed for the proof, something like that, where you could say, my guideline is you shouldn't pass this threshold, and this threshold is somehow meaningful to you. I guess this is related to works on decidable fragments and EPR, where we sort of have a different version of that in terms of a quantifier alternation graph. But I'm wondering if there is something like that. And of course, ideally, you would want to have something where you can have a guarantee that if you meet this threshold, then Z3 is stable. You won't have to worry.
So I think that the most relevant user-facing metric for stability is, does the proof have varying verification outcomes, right? The real and downstream thing that you want to prevent is one day the proof checking and one day the proof failing, right? And these variants, sort of the coefficient of variation, does seem to sort of empirically correlate with downstream variance in actual verification outcome. So I really do think that this is actually a pretty good proxy. And it's also sort of directly measurable by, you can report this to the user for sure. The fact that it's opaque and not sort of directly related to any particular syntactic metric is frustrating, that you can't sort of like, you have too many for alls, go fix your for alls. You have too many ors, go fix your ors. That's a little annoying, but I like the fact that it's at least quantitatively measurable and correlated to something that is really quite bad.
Suppose that you had a different starting point. Suppose that there was a change in Dafny when you started, and all functions were opaque. Then you would have been forced to have done something like this to begin with. Wouldn't that have satisfied things? Would you have fleed the automation goodness for some older proof assistant for that?
That's a great question. I think that's a really, really good question. I think probably not. Although there's certainly, that's a really good question. I struggle to speculate about my mental state from 2 years ago, but I do think that there's a good chance that I would have taken the time to think about exactly what the proof needs to look like instead of sort of forging ahead. I think that there's a sort of confidence that comes with the great automation, like the amazing automation that Dafny has, where you just like, you get one small win with like, we built this incrementally. You started with a small version of the language, and it all just worked. You just call the IH, and everything just checks. And then you start building it out to extend it to the rest of the language, and it slowly starts to degrade. And then you have to make a decision. So I think the thing that was the issue was that it was too good at the beginning. And if we had had the ability to make this different decision earlier, that would have been good too. Thanks, everybody.